and want to review, because we can do as much or as little as you want to. We can go through the answers for sure. But what we're going to focus on here are the volumes of revolution. All these problems are volumes of revolution. So we can do them with disc washer situation, or we can do it with this alternate thing we learned yesterday, which is the shell. So when we look at problem number 4, which you were supposed to revolve around the x-axis, I believe, and you were supposed to use the shell method, what'd you get for the answer on this one? 8 pi thirds. Okay. Now, if you're revolving around the x-axis, which way does the strip have to be for the shell method? Parallel. So it's got to be horizontal. Now, this equation was y equals 2 minus x, but if we're going to do horizontal, we've got to solve that for x. So we add the x over to the other side, subtract the y, so we get this. So if we're going to do this with the shell method, we got to write down what p and h are. So h, of course, is the right x-coordinate, it's just the length of the strip, so that'd be 4, minus the left x-coordinate, which is that equation. Now, when you get one like that, it's probably better to simplify it, so that'd be 4 minus 2 plus y, so that equals 2 plus y. You don't have to simplify it, but it's probably better. And what would the p be? Because p is this distance. Now, somebody was asking me, they said, so in shell you have 2 strips, a horizontal and a vertical. Well, I guess so. I usually think of just this as my strip. I don't think of this as my strip, but I do think of it as a top minus bottom situation. So this y value, if this y value, say, is at -1, if the strip's at -1, how far is it from the center? Well, 0 minus -1, which would be positive 1. So it's 0 minus y, which would be -y. That's true. So our shell method is 2 pi times p times h dy, and the strips go from -2 to 0. Okay, now, if you had your choice, this would have been a pretty easy one to do. I think it's good to practice both. In the red here, let's do this as just a plain old disc. Now, so keep in mind, if you've got a horizontal revolution, axis of revolution, here's your shell. It's got to be horizontal. It's got to be parallel. But if you want to do a disc, it's got to be this. So the slices would be this way. Okay? So this would be a pretty easy one to practice and just look at. The radius would just be this, which would be 0 minus that curve, except now we got to use this one, this y value. So that'd be -2 plus x. So our integral would just go from what, 2 to 4, and then it would be pi, and then the radius squared. So you could type this in and type that in, you better get the same answer, 8 pi thirds. Okay, what about this one? What way is the strip going? It's got to be vertical, right? If you're going to do shell method. Now, and you were supposed to do shell method, so you probably never thought of doing anything different. That's fine. So h is going to be that strip. It'd be this one, which is the 4x minus x squared parabola, minus this one, which is the x squared parabola. Okay, which would be 4x minus 2x squared if you want to simplify. What would p be on this one? Just x. Because if this strip is at 1, how far is it from the center? 1. If the strip is at 2, how far is it from the center? 2. It's just x minus 0. It's just the x location of this strip minus the center, x minus 0. So it's just that. So we got 2 pi, we got p, make sure you put a time sign there. We got 4x minus 2x squared, and the strip fills the space from 0 out to what, 2? And what was that, 16 pi thirds? 16 pi thirds for that one. Now, somebody in the other class asked about this one. Now, if you were going to do a disc washer, what would it be? Well, there'd be empty space here, right? So you would have a radius that would go to the outer edge, and you'd have a radius that would go to the inner edge. So we didn't think too much about it, but then all of a sudden we started thinking about this. We said, well, okay, if you're going to write your big R, that would be this equation. So solve it for x, you get x equals square root of y. So big R would be this x coordinate, square root of y, minus this x coordinate, 0. What about little r? What's this x coordinate? Could you solve that for x? Well, if we tried it in the other class, we tried solving this for x, and it did do it. It came out to be a messy thing. Then we changed it to x cubed and tried to solve it, and then it was a real disaster. I mean, it was arc sines and cosines, and it was just ridiculous. And some of them, like this, if you ask the calculator to solve it for x, it will just spit it back at you, and it won't even be able to do it. So this is another reason why we have the shell method. We have an alternate method. There are some times where horizontal strips just ain't going to work. You're going to get an equation where you cannot get the x by itself. Now, there are some workarounds and some things you can do, but we're not going to want to have to deal with those. So having shell method as an option allows us to keep vertical strips, which is good because then we don't have to solve for x. Okay? So this one was much, much easier with the shell method. All right, as opposed to number 12. Number 12 would have been way easier to not do the shell method. If we could have just done a regular old disc right here, right, perpendicular to your axis of revolution. Here's your axis, so here's your slices. This would have been way easier to just do a radius. This is what y equals 1 over x. So this would have been way easier to do 1 over x minus 0 and done the integral of pi radius squared from, what, 1 to 2? That would have been a piece of cake to do number 12, but you weren't supposed to do that. You were supposed to do it with the shell method. Now, number 12, they got an answer of pi halves. Okay? Well, here you got to split it, right? We mentioned that yesterday. So right here through the middle, or kind of through the middle, you're going to have to split that. And that's right there at 1/2. So let's just review that real quick. So you're going to have a strip here, and you're going to have a strip here. Okay, so the h's are going to be different. Now your p's will be the same, right? Y minus 0, y minus 0. So p either way is going to be y minus 0. But on your first one, the top one here, h is going to be that. Now we're going to have to solve for x. Multiply the x over, divide the y over. So that's basically similar. So it's going to be 1 over y minus 0. Yeah, minus 1, thank you. Minus 1. And on the bottom half, okay, hang on. What do I need to do? Get rid of that. Get rid of that. Okay. All right. So h on the bottom one is just going to be 2 minus 1, right? So our our bottom integral is going to go from 0 to 1/2, right? The strips are going to fill this space from 0 up to 1/2, 2 pi out in front, and it's going to be p, which is y, times h, which is 1. So that's the bottom half, plus top half is going to be 2 pi. It's going to go from 1/2 to 1, and that's going to be 1 over y times y. I'm having trouble with that minus 1. Okay, 1 over y minus 1, there it is. Okay, 1 over y minus 1 times y. It's going to go from 1/2 to 1. So it's messier doing the shell. So we saw on the previous one, shell was by far better. You really couldn't even do it the other way. And on this one, the disc method was by far better. And I really think on my quiz, the quiz next week, I'm going to let you choose. Okay, I'm just going to give you the region and say find the volume. And so you do whichever one you want. And again, do them both if you want. Now, if you come up with different answers, you better pick one. Okay, don't leave them both on there. But if you get the same answer on both, then you can go with it. Okay, 17 is very much like the one we did the other day. If we were going to do a shell method with this one, we'd have a vertical strip, so that's going to work nicely. This is square root of x. So we're going to have our h is just that strip, so it's square root of x minus 0. But what's the p on that one? 6 minus x, because here's your strip. So if your strip's at 2, if your strip's right here at 3, how far is it from there? 3. 6 take away 3. Right? If it's at 4, it's 2 away. 6 take away 4. So it's 6 take away x. Okay? So 2 pi, 6 take away x, times square root of x, and the strip fills the space from 0 to 4. It doesn't go all the way to 6. The strip only goes from 0 to 4. Okay? If we were going to do a disc washer with this one, we would have big R, because there's empty space, little r, like so. Okay? And we would have to do horizontal strips. All right. And just because of time, I'm not going to go through all of these on this one. We can look at the answers, but 17, or you can look at the answers. 17, what was that answer? That was 192 pi over 5. 192 pi over 5. Now, 21's a good one. Now, next week, when it's time to practice, 22 would be a good one because it's got some other ones, you know, that you can just do. But on 21, we had these 4 parts. So on this one, if you wanted to keep vertical strips, then what would this be shell or disc? This would be disc, right? And that would be a good way to do this one. But if you want to do shell, if you prefer shell, it's not a bad one to do shell either. They're pretty easy equations to work with, but you'd have a horizontal strip if you were going to do shell. Either way is pretty equally easy on 21A. On this one, if you want to do shell, you're going to have vertical strips, right? If you want to do the disc washer, you're going to have empty space. So your big R would be there, your little r would be there. It's up to you. Again, do them both ways. Good practice. All right? On C, now we're revolving around here. Once again, if we're going to do shell, we would have vertical strip. If we're going to do the disc washer, we would have outer radius. We would have inner radius. Okay? All right, and then the last one in part D, if we were going to do shell with this one, we would have to have a horizontal strip. If we were going to do the disc, we got this empty space. So we're going to have an outer radius to there. We're going to have an inner radius to there. Okay? From the center. Radius always goes from the center. All right, so that's pretty good summary. Those are some really good ones to practice this volumes of revolution, which are the ones we run into most often. Disc washer, if you want to do the perpendicular strips, the slices, or if you want to do the shell method, you have parallel strips, and those are your options. Then, of course, we have these ones on the base, which those are pretty easy. You just draw your strip, and whatever the strip is, that's one part of whatever those slices are, and you just got to know those, okay? So that's pretty much it. Those are your volume problems, and we'll review that again next week before we do our quiz. All right, so let's get your notes out, and let's talk about the new business we have to do here today about this thing called work. Now, do you guys do in physics very much with this? You do spend some time, okay. Because I wasn't, it's been a long time since I've looked at the physics book, and I don't know how many different examples you do of it. So it seems like, I don't know if there's converting of units, and maybe there's a lot of that kind of thing. Because there really isn't much to the formula, right? That's pretty much it, isn't it? Work is force times distance. Now, maybe you have some other things in finding your force and so forth. But so a typical problem would be something like this. I'm going to take a 10-pound book off the floor, lift it 7 feet up over my head, right? Not 7 feet over my head, but a distance of 7 feet from the floor. And that would require 70 foot-pounds of work to do that. The force is the weight of the book. Okay? So pounds, so our force is measured in pounds. Now in science class you use metric units, probably so you use newtons for force, typically, is that right? And so it'd be like Newton meters would be the units. But in our book, it's always feet. It's English units, feet and pounds. So we'll use foot-pounds. Okay? So that'd be 70 foot-pounds of work to do that. Now, if I stand there and hold a book or some heavy object over my head, even though it's, hard to do, and, at some point I'll, maybe drop it, whatever, am I doing work? No. There has to be a movement through a distance for there to be work. So if you take something really heavy and you stand there and you're holding it, feels like you're doing something, but you're not doing work, okay? Because work has to be a force through a distance. So the act of picking it up and lifting it up to this point, that's the work, okay? So 70 foot-pounds. It's very simple. You just multiply those. Now, here's the difference, and I talked about this before, between high school physics and college physics. College physics would be a calculus-based physics. Well, one of the differences is when you do motion problems. In physics, all your formulas about velocity acceleration have to do with constant acceleration. So, for example, average velocity is initial velocity plus final velocity divided by 2, right? That's only true if you have constant acceleration. If you have variable acceleration, that doesn't apply. You need calculus to deal with that. Well, the same thing's true here. Because, for example, you weigh different weight here than you would on the moon. Why? Because of gravity. The weight, your weight is a force because it's the force of gravity, right? What about your weight here compared to Mount Everest? More where? You weigh more here than on Mount Everest. Why? Closer to the center of the earth. The gravity is actually more here. Now, is it measurable? It's very tiny difference. It's a very tiny difference. But there is a difference. There is a difference, right? So, when you do this problem here, technically, when I take a book that weighs 10 pounds on the floor and I lift it over my head, it weighs less when I get it up over my head. Now, it might be in the 700th decimal point, but, right? And so in physics, high school physics, they would just ignore that difference. And in calculus, we would actually ignore that difference too, if you're only moving at 7 feet, okay? But there is a variable force in it. So as I pick up this book and I move it 7 feet, technically, theoretically, that force is actually changing. It's actually weighing a little less as I get it up to that 7 foot distance. Now, like I said, we're not going to ignore that, but that gives you an idea of variable force. So if you have a constant force, then force times distance is just your equation. It's very simple. But if you have a variable force, then you can't just take force times distance because that force is changing throughout the distance. So guess how we use calculus to do that? We're going to do an integral, and we're going to break it up into little pieces. In other words, we're going to say, okay, what if we took that book and only went a foot and did the work, and then another foot, and then another foot? Well, technically, the book is still changing weight in that foot. So let's do it every half foot, or let's do it every 4 inches, or every 1 inch, or every half an inch, right? And so pretty soon what you find is the distance, we're breaking up into smaller and smaller pieces. The distance is going to become the dx part of the integral. And it's like what we're going to do is use the integral then to add up the little bits of work we do for those little tiny distances until the tiny distances are just razor thin distances, kind of like we did arc length. Instead of doing the whole arc length, we do little tiny bits of distance, we add them all up. So it's that same concept of what's going on. So our formula is going to be this. Our formula is going to be, well, it's not really even a formula. Our force equation, now when I say force equation, I mean our pounds, our equation for pounds. And this is just going to be the distance. The dx is just going to be the feet. And so that's why our integral is going to be foot-pounds. So when we see big F of x, we don't want to think antiderivative or anything. We want to think force. Okay? We want to think force. So we want an equation for pounds. Okay? Now, how do we get that? Well, we're going to keep it pretty simple. We're going to do two examples. One's really simple, and then the other one gets a little more complicated, but it's not too bad either. So what we need to do is set up an integral that has pounds in it, and then the dx will be the feet, and that'll give us foot-pounds. So the first example we're going to do is a spring. Okay? So the way we're going to get pounds when it comes to a spring is something called Hooke's Law. And basically Hooke's Law just says that if you have a spring, okay, think of a slinky or something like that, and I think of something a little more rigid than that, but that's sort of a thing. Okay, and if we're going to stretch or compress a spring, Hooke's Law says basically that's a linear formula for how hard it is, how much force is required to stretch or compress it. Okay, so K is like called the spring constant. All right, so here's an example. So if we have a spring whose natural length is 3 feet, now we don't want to think about stretching both ends of a spring because that just complicates it. So let's imagine we've got a spring that's attached to the wall here, and we're going to stretch it out from there. So this spring is going to stick out from the wall 3 feet. Great big old spring. And it's just 3 feet, and then we're going to stretch that out from the wall. So we're going to stretch it out to 5 feet. And that takes 10 pounds of force to do that. So you'll always have to be given this in a spring problem. Spring problems are pretty easy, pretty straightforward. So you're going to be given how many feet you have to stretch it, how much force it's required to do that, and that's going to give you your force equation for that spring. Okay? So, what would K be? No. It would be 10, your force is 10 equals K times 2, right? So 2 feet's how far you're going to stretch it, right? 2's the feet. So you're going to go from 3 feet to 5 feet. So you're going to stretch it 2 feet. Now another way to think of the K is it's pounds per foot. So if you're going to stretch it 2 feet and it takes 10 pounds, you can just divide that and say, well, it's 5 pounds per foot. So your equation is going to be 5x for that particular one. That's going to be force. It's 5 pounds for every foot. It takes 5 pounds of force for every foot. So 5 pounds for the first foot, another 5 pounds for the next foot, another 5 pounds for the next foot. Okay? And so that's the pounds of force required. And so that's going to go into our integral. So for a spring, for that spring problem on that previous page, it's simply going to be 5x dx, because this is pounds and this is feet, right? Remember the 5x is pounds because the 5 was pounds per foot, the x was feet, so that's pounds, and then the dx is feet, so it's going to be foot-pounds. And then now, the integral on that last problem would be from what to what? How much work was done? It would be 0 to 2. It would be 0 to 2 because the natural length of the spring at rest, is 0. So if the spring has a natural length of 3 feet, that's our 0. And we stretch it out to 5 feet, we went 2, so it's 0 to 2. Yeah, if you did the integral from 3 to 5, that would be different. That would mean you went from a stretch of 3 feet to a stretch of 5 feet. And that's not what we had in this problem. We started with 0 feet stretched out to 2 feet stretched. No. Well, no. So if it's 3 feet naturally, you stretch it out 3 feet, now it's at 6. See what I mean? And that would be different. That would take a lot more work. It's because the more you stretch it, the harder it's getting, right? So if you get out, if you're out and you've stretched it out 3 feet, and then you stretch it out 2 more feet, there's a lot more work moving those 2 feet than there were the first 2 feet. Does that make sense? So that's what's going on there. Yeah, it gets harder and harder and harder as you stretch it. So that's why it is a different answer no matter what. So yeah, if you did the integral 3 to 5, that's a different situation. You get a much bigger answer because it takes more work. Okay? So that's the important thing in getting these numbers here. Okay? So that's it. I mean, that's every spring problem is going to look like that. It's going to be a simple linear equation in here. It's going to come from this Hooke's law, okay? And you're always going to have to be given this kind of information. You're going to have to be given for that particular spring. They might just tell you the spring constant, which tells you the K. Or normally what they'll do is they'll tell you it takes this many pounds of force to stretch it this far. How much work is done? They might just say, like in this one, how much work is done to stretch it that far. Or they might give you a different distance. They might say how much work is done to stretch it from 3 to 4. So there we would have went 0 to 1 in our interval. Okay? All right. So that's the simplest example, is the spring example. Okay? So we'll look at that one. So we'll have some homework on that one. Here's the next problem. Here's the other type we're going to do. The rope and bucket. The rope and bucket problem. So we got a well that's 20 foot deep. We've got a bucket filled with 2 gallons of water. And the rope, the 20 feet of rope weighs 1.6 pounds. How much work is done in raising the bucket? So we're going to lift this rope, lifting the bucket up 20 feet out of the well. Now again, our X will start at 0. There, 0 is at the bottom of the well. That means we haven't pulled up anything. We haven't lifted anything. X is how far we've lifted it. So it's going to start at 0 down there, and it'll be 20 up there. Maybe we should call it Y since it's vertical like that. But whatever, doesn't matter. So X is going to be the feet that we've moved it. Okay, well, now we don't have a formula like Hooke's law, but all we're going to want to do is we're going to want to make an integral that is pounds, and then the dx is going to be feet. Okay, and that'll give us foot pounds. So we need to just write down what it is that we're lifting, how many pounds we're lifting. Well, what are we lifting? The bucket, the water, and the rope. Are any of those changing? The rope. Now, in high school physics, you would ignore the rope. Now, that's one we're not going to ignore. Now, also, again, like we said, the water and bucket weigh more at the bottom than they do up here because of gravity, but we're going to ignore that because it's not even measurable. But the rope is measurable. We're not going to ignore that. Like I said, in high school physics, you would ignore the rope. But the rope, with every pull of the rope, now you're pulling up less rope, right? So it weighs less with every pull. So that one is going to change. What's the other information we need to know? How much the water weighs. Let's say it's 5 pounds per gallon. I'm not sure what it is, but that sounds good. Let's say you would have to be given that. Okay, like density, would that be density? Yeah, but isn't it volume? Oh yeah, in water, right? Yeah, I think I've got something on the density of the. It's more like 8 pounds per gallon. Yeah, let's use that. Let's use 8 pounds. I think that's more accurate. But isn't it mass divided by volume? Yes. Isn't that density? Yes. Right. So 8 pounds, we treat that as mass divided by volume. So basically you'd have to be given that so you would know. All right, so that means we have what, 16 pounds of water? Okay, so we have 16 pounds of water. All right, so here we could do 5, since that's not going to change, so that's our bucket. Okay, plus 16, that's our water. So as we lift it up, that's not going to change. Plus our rope. Now that is going to change. So we're going to need an equation there. So we need an equation that's going to be pounds of rope. Something will have to be negative in there. I don't think the pounds will be negative because, you know what I mean? But right. So I think we need the pounds per feet. It's going to be a linear. We're going to treat it as a linear situation, right? as the rope's coming up, we're losing so many pounds for every foot we come up. So couldn't we just, so there'll be a couple ways to do it. I'm going to show you, let's just think our way through it first, and then I think I'll show you a way that you might like better just to do. But so what would be the pounds per feet? 1.6 over 20, which would be 0.08. Now, isn't that what you mean would be negative?
Yeah.
Right, that would be negative, right. Isn't that kind of like slope, though? Yeah. I mean, that's basically what it would be. Now, what's the equation then? Not quite. Why is it negative 0.08x? Because what does x represent? Number of feet we've moved it.
So 20 minus that.
So when x is 0, how much rope do we have? Well, how many pounds? 1.6. So when x is 0, we want this to be 1.6. So we can't do 0.08 times x. Then otherwise that'd be 0.08 times 0. We'd have 0. So it needs to be 20 minus x, like that. So when x is 0, we have 20 feet of rope. So negative 0.08 times 20. And when x is 20, we've lifted it all the way up. We have no rope left. So when x is 20, then this would be 0. So that's how you could get it by just thinking your way through it. And it's always going to be a linear situation. So it's a lot like the spring problem, which is a linear situation. The 5 in the last problem was the pounds per foot of force, right, that keeps increasing every time you stretch it. Here we have this. Now, some people have struggled with this over the years, so I've come up with another way you could do this, is to just think of it as a couple of ordered pairs, the beginning and the end. So think of the rope, again, think of x and y. Remember, x is feet. So this is feet and this is pounds. So just think of the beginning and the end for the rope. So at the beginning, how many feet of rope? No, because remember at the beginning, x is how many feet we pulled up. So it's 0, and what's it weigh? 1.6 pounds, right? At the end, we've pulled up 20 feet, and it weighs 0. Now just do an equation using those 2 points. So you do a slope, so it'd be 1.6 minus 0 over 0 minus 20. So you get 1.6 over negative 20, which is negative 0.08. And then, oh wait, time out. I did this wrong right here. Yeah, that can't be negative. I don't know why. I was getting ahead of myself when Brock said it was negative. It's going to end up negative when we multiply by that x right there. So this has to be positive right here. This has to be positive. This is 0.08 pounds per foot times this many feet. So that's going to be that many pounds. So yeah, the 0.08 will end up being negative. But so on this one, I should have kept that just positive. Okay, so that was wrong. But right here, it's negative. Okay, because I'm going to set this up different. So now I'm going to do my equation just the way we've done it. So I'm going to take my slope, which is negative 0.08, and then take one of my points. I'll take that first one, x minus 0 plus 1.6. Now notice how that comes out the same. You get negative 0.08 plus 1.6. Isn't that the same as that right there? If I distribute 0.08 times 20, I get 1.6. And take 0.08 times negative x, I get negative 0.08x. So for some of you, you might prefer that way of doing the rope. Say, okay, I'm going to start with 0 feet lifted. The rope weighs 1.6. I'm going to end with 20 feet lifted, and the rope will weigh 0. And then just do a slope with that. Pick one of those points, write your equation. That gives you your rope equation. Okay, now, let's, anybody type that in yet? Somebody type, oh, what's the integral go from where to where? 0 to 20. Because remember, that's feet. Okay, so type that in, would you? And while you're doing that, I want to do the high school calculus, or excuse me, the high school physics version of this, where they would ignore the rope. So they would have 21 pounds of water in bucket times 20 feet. And that would be 420 foot-pounds. Right? So if you ignore the rope, it would take 420 foot-pounds of work to lift that up. If you do our integral, 436. A little more work because you have that rope to haul up as well. Okay? All right. Now, let's consider this. Now the bucket's leaking. So it starts with 16 pounds at the bottom, but when we get it to the top, it's empty. Now, we're going to assume, again, to keep it simple, a linear rate that the water comes out. Because remember, we did that differential equation problem. Remember Torricelli's law with the cooler, with the thing of water? It comes out faster when it's full and not as fast at the end. So we'll ignore that, and we'll just pretend that it's going to come out the same rate all the time. Well, think about that. Bucket is, remember we want pounds here, and the dx is going to be feet.
Bucket's 5.
So the bucket doesn't change, so that's 5. The rope we already figured, so I'm just going to keep that same equation. What was it, negative 0.08 x plus 1.6? Yeah, I went ahead and used the other version we had, whichever, or you can put 0.08 times 20 minus x, whatever. Either one of those. And now we got the water, and the water is going to change now. But isn't it going to be the same thing? Yeah, it'll also be negative slope, but we could do it with an ordered pair. We could say, okay, when there's 0 feet pulled up, how much water? 16 pounds. And when there's 20 feet of rope pulled up, there's 0 pounds. Now, sometimes you'll get these problems like the one in the homework, I think it might say, when it gets to the top, it's half full. So, 20 pounds, or 20 feet, and you'll have 8 pounds, right? And then, so I like this, just doing an ordered pair. So again, we can do 16 minus 0, 0 minus 20, so that's negative 0.8. So it would be negative 0.8, and then pick one of those points, x minus 0 plus 16. So that's negative 0.8x plus 16 is your water. Or like we did earlier, you could do just 0.8 times 20 minus x, right? 0.8 times 20 minus x. 0.8 is the pounds per foot that you're losing times 20 minus x, which is the feet that's been pulled up. Or the feet that's left, the feet of. So this time you have 2 of them that have equations because you have 2 of them that are changing weight. The rope is changing weight as it comes up, and the water is changing weight as it comes up. And you get those 2 situations there. Okay? So, those are the 2 types of problems you're going to have. On the quiz next week, for sure, you'll have a spring problem. That's the simplest kind. And I don't know, it depends on how long we have for the quiz, because that is the day that we have the 2-hour late start with the NISA testing and stuff. So if I have to leave one out, I would leave out the rope and bucket one, but I don't think it's terribly tough. But you're going to get to practice a few of them in the homework. Okay? Now, the last situation we're not going to do. I was so proud of the fact I was able to copy and paste this into here that I hate to not do it. But this is pumping liquid. How much work is done to pump this liquid out of this tank up to this hose? And how many horsepower motor would you need to do the work to pump the water out of there? But it's kind of messy.